All right, so today we're going to finish up graph algorithms by talking about the Floyd-Warshall algorithm, which is another shortest pair or shortest distance, shortest weighted distance algorithm. But instead of Dijkstra's, where it starts at a single source vertex and then gives you the shortest distance to all other vertices, this one computes all of the shortest distances all at in one shot. And it does it through matrix, not multiplication, but matrix transitive closure operations. So let's take a look over here at this simple graph and explain what the basic idea of Floyd's algorithm is. So forget about the actual graph here for a moment, but consider any two vertices, V to, say, W. Okay? So I want to know what the shortest path is from V to W. All right? So to do that, what I'm going to do is I'm going to consider, well, wait a second, what if I went from, well, first of all, if I can get there immediately, then you consider that path. But you're going to consider other intermediate paths, right? Well, what if I go from, say, I'll rename these here, because that's what we're going to rename them in the algorithm, V sub I to V sub j, right? What if I go to V sub k first, and then from V sub k, I go over here to V sub j? Now, what if I ask that question over and over again? What if V sub k was V1? What if it was V2? What if it was V3? ... until I get down to V sub n. Right? Now, some of these endpoints are going to match each other. Sometimes this one will match this one, and sometimes this one will match this one, right? But if you ask this question over and over and over again for each possible midpoint from Vi to Vj, right? Then you will eventually get a better, or that you'll eventually find the shortest path, right? Now again, this is an entire path. What is the weight of going from V sub I to V sub j, or Vk, excuse me, and then what's the weight of going from Vk, your midpoint, over to Vj, right? And so the total is going to end up being the addition of those two things, right? And if that's better than what you found so far, right? If that's better than the weight from, say, Vi going directly to Vj without using Vk as an intermediate point, if whichever one's better, that's the one that you take and that's the one that you keep track of, right? That's the idea. So let's just look at a preview of this idea with this simple graph right here, okay? For example, I want to go from A to E. All right, this is our first example. I want to go from A to E. Well, first of all, if I consider A as its intermediate point, in other words, is there an edge directly going from A to E? Right? No, you can consider that as a weighted edge of infinite weight. All right, so that establishes our baseline, right? I can get there at an infinite weight. All right, well, now ask the question, can I go from A to E using B as an intermediate? In other words, I will go from A to B and then B to E, right? Well, what's the weight there? 1 plus 3 equals 4. Oh, sorry, you're right. Undo that. Come on. 2, and then that's equal to 3. Right? Is that better than what we found so far? Remember that thing? That's infinite, right? Well, anything finite is going to be better than infinite. So yes, this is a better weight. Okay. Is there an even better way? Well, no. You fast forward and ask the question of, well, what if you use, say, C as an intermediate? No. Well, what if you use D as an intermediate? What if you used E as an intermediate to get to E, right? You ask all those questions. What gets really interesting is when you start asking questions like, say, A to D, right? So initially, is there any edge going from A to D? Nope. So it's infinite. Okay. But what if I ask the question, well, what if I go from A to B and then to D? Well, it's not going to be recursive, but it will be kind of dynamic. I'm just asking the same question over, well, what about C? What about D? What about E? Dot, 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 right? Those are the questions I'll eventually ask. But I'll start with B. Right? So if I go from A to B, and then B to D, what's the cost there? 1 plus 8 is 9. Okay. That's going here, and then, well, undo that. That's going through here, and that's better. So we'll erase this old path over here, which was infinite anyway. Okay. All right. Well, now start asking another question. Well, what if I used E, right? A, some path to E, and then on to D. Okay. Well, we've already established what's the minimum path to E. 3, right? This is going from A to B to E, right? E right there. There's your path there. Now, can you go from E to D? Yes. At what additional cost? 3. So in total, 6, right? And so you say, okay, well, yes, we're going to establish that E is our midpoint for that that path, that shortest path. That's as best as you can do, by the way. 1, 2, 3, 6, going around circuitously here around B gives you a better path than if you had gone through B. Well, what if you ask another question? All right, we asked that about E, right? Before that, we would have asked about what? C. What if we went to C instead first? Right? A, 2C, 2D, right? That was going to be 2 plus 5, which is 7, right? This is the eventual one that we'll answer as the best, right? So you do this over and over again for each pair of vertices. Right? And that leads to Floyd's algorithm, right? Floyd-Varshall, whatever you want to call it, okay? Here is the initial, here's the pseudocode that we'll reveal here in a second. But understand that what the input is. It's a weighted graph, but it's in the form of a matrix, an adjacency matrix. So let's come over here, and let's understand what that looks like for this graph. Okay. So first of all, what you do is you establish a. Oh, no. Oh, okay. Well, that's kind of matrixy, right? But I'll go ahead and draw it like this. You establish an ordering on your vertices. Now, in this case, it's just going to be lexicographic order: A, B, C, D, E. A, B, C, D, E. And now, since this is a directed graph, it's not going to be equal to its transpose. It's not going to be symmetric, and the adjacency entries here are going to be infinite if you can't reach it. Otherwise, it's going to be the weight. For example, you can go from A to B at a weight of 1. A to B at a weight of 1. What about A to A? If you're already in A, what do you leave? No. So what's the weight? 0. Right? A to C, you can get there at a weight of 2. A to D, you can't get there, so it's a weight of infinite. A to E, weight of infinite. B only has 2 outgoing edges to D and E, so that's going to be 8 and 2 respectively. Along the diagonal, it will be zeros, but otherwise everything else will be infinite. C only goes to D at a weight of 5, so make sure that you've got zeros here on the diagonal. 1, 2, 3, 4. There we go. Otherwise, infinite everywhere else. There we go. D has 1 outgoing edge to B at a weight of 4, so infinite everywhere else. There we go. And then E has 1 outgoing edge to D at a weight of 3, infinite, infinite, infinite. There we go. That's your initial matrix. Okay. There. So we're going to call that D. Right? Now that you can be given that as part of the input if that's your graph representation. Otherwise, within the implementation itself, you can go ahead and formulate your own matrix like this. Okay. Now what we're going to do is we're going to initialize everything, right? Like we just did. If you can go from I to J, that's going to be the weight from V sub I to V sub J. Right? Otherwise, it's going to be infinite if there's no such edge. Right? That's what we just did for the first for the first iteration of this, or the initialization iteration. Right? I'm going to replace that with, let's see, graphs, Floyd. Oh, I don't have. Okay, so no, I didn't bother taking a screenshot. That's the best screenshot that I have. Right? Okay. So and we also need to initialize what's called a successor matrix of S. So because we want to be able to rebuild the path once we're done, right? Remember that this one, eventually we're going to say, well, the shortest path from A to D is going to go to B to E to D. We need to keep track of that information. That in order to get from A to D, you need to first go to B. Then you need to go to E, right? Then you can go to D. And that's going to be called the successor matrix. Success or matrix. Right. S sub ij. Now the entry ij is going to say that to go from v sub I to v sub j, you first go to S sub ij. That's what that entry is going to be. What does the initial configuration look like here? What do you think? It's going to be, most of the entries are going to be nothing, right? Right. So, oops. Sorry. Let's go over to the code here. You initialize the successor matrix S by setting S of ij equal to j for all edges that are present. So if there is no edge present, then, for example, every time that you have an infinity here, that means that there's no edge, and so you would end up saying nothing, nothing, nothing. Otherwise, you can go from A to A with the successor of A, right? B, C, D, E, right? The rest of it is going to be S of I, J. It's just J. Right? So in other words, you're going to fill each column with itself. Right? So each column, if there is an edge, B, there's no edge, B, no edge. No edge, no edge, no edge, no edge. There, right? Whatever that was. Otherwise, C, no edge, C, no edge, no edge. Now I'm on the column for D, so that'll be D, no edge, D, 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 and D. Otherwise, no edge, E, no edge, no edge, E. That's the first one. This is S1, and this is D1. Right? That's the successor matrix. We are going to make changes to this, and we're going to make changes to this as we go through the algorithm. Like I said before, all you need to do is ask questions about each intermediate vertex. Right? Here's the picture that we drew. V sub k. You want to know for each v sub I, if I went and used v sub k as an intermediate at a vertex, and then went on from there to v sub j, what is that better than what I've found so far? Okay. And so to get for each pair, I and j, we need another for loop. For each I, running from 1 up to n, for each j, running from 1 up to n, we ask the following question. Right? Here is or what's the new distance? Is it the old distance that we've already found so far? Right? So let's annotate that. This is the best, that is the least weighted distance so far. And this is the distance using v sub k. In other words, this picture up here. Right? Now, if that distance is better, whichever distance is better, that's the one we update it with. Right? So, if it's updated, then we also update the successor matrix value, right? Because this says that, okay, well, to go from v sub I to v sub j, you first need to go to v sub k. And so whatever the successor was for v sub k, right there, that's the one that we want to take next. So let's come over here and The first iteration, I don't think it updates to anything, does it? Because we're going to ask the question about using v sub or a, and a has no incoming edges, right? So forget about a. Instead, let's go on the second iteration of this loop where v sub k ends up being b. In other words, this one right here. That's our intermediate, okay? We won't look at all of them, but let's look at the one that we were looking at before of going from A to E. Right? Remember, it was infinite before. Now, what is it? It's going from A to B, 1, and then B to E. That's going to be B to E. That's 2. So 3. 3 is better than infinite, and what do we get? What do we update it to? 3 right here. Right? But what else do we update? The S right here. What was your successor value? If you went from A to B and then on to E, right? You need to use B as your successor value. Right? And there. Come on. B. Right? A whole bunch of things changed throughout the algorithm. I've got 5 here, so looking at this algorithm, how many iterations does it go? 5 times 5 times 5. Do we want to do 125 different values? No, I don't want to, at least. Instead, let's just go ahead and look at the final values here. Right? Here is the final distance matrix. Right. There we go. How did so for example, going from A to E at a cost of 3, that never changed after that first iteration, right, with B. Right? But what about going from, say, A to D? Right? Initially, we said, oh, well, you can get to there for using B at a cost of 9, right? 1 plus 8. But then in the next iteration, when we used C as the intermediate vertex, we would have said that, oh, well, you can get there at a cost of 7, right? Dot, dot, dot. A to D ultimately was 6. Why? Well, when we asked the question, well, what happens when you use E as an intermediate vertex? 1 to 3, 1, 2, 3 total, and then finally 6. Right? How did we keep track of that? Here is the final successor matrix. Right, there we go. So again, how do I go from A to to D here? Right? What I'm interested in is A to D, this one right here. Right? What that answer is that you first go to B. Okay, I want to go from A over here to D. The first thing I need to do is go to B. Now that I'm at B, though, how do I get to D? Well, if I just jumped here immediately, I would have a cost of 9. That's what we would have had in the first iteration, or the second iteration of the algorithm. I don't want that, right? So I look again at the final successor matrix. How do I go from B to D? Well, that one is right here, B to D. Right? Tells you to go to E next. Right? Now I'm at E. Right? I want to go to D. Right? So E to D gives you, these should have been just, oh no, sorry, E to D. There we go. There, D. Right. So in other words, you just go to it. How do I go from E to D? You just go to D. Right. And so by bouncing around here from this entry to, what was the next entry? B to D, so then this entry, and then this entry, jump to this entry, I was able to rebuild the path. Right. So again, there's the algorithm. Yeah?
So, if you haven't found out that you can go to D from B through E. If you haven't found it out, will you eventually find out about it?
Yeah, you'll find out about it not on the second iteration, not on the third iteration, not on the fourth iteration, but on the last iteration. So these matrices can potentially change each and every single iteration, right? Sometimes they might not change, but then the next iteration they will change because the question changes, right? The question here is, what if you use v sub 1 as the intermediate vertex, v sub 2 as the intermediate vertex, v sub 3, right? Or in our numbering system, it was, well, what if you use A? What if you use B? What if you use C? Right? Okay, so there is the algorithm. It's just 3 simple for loops. So guess what the complexity of this is. Yep, this is order n, order n, order n, and the elementary operation here is just a conditional, right? It's a comparison between these two values, which one is less, right? Maybe you have an update here or not, right? But otherwise, altogether, it's going to be order n, order, order n cubed. There we go. Is that better or worse than Dijkstra's? Well, Dijkstra's was what? M plus n or something like that. We'll just go ahead and go with order m. All right, but that was for Dijkstra's, for one source. Right. If you want to do it for all n vertices, it gives you, yep, order n m, which is basically n cubed. So pick your poison, right? Do you want to work with matrices or do you want to work with a heap, right? It's all up to you, right? Now, there is one missing piece of the puzzle here. Given this successor matrix here, how do we go about building that, that path, right? For example, like what I just did. If you want to go from A to D, first of all, you need to go to B. Well, if you want to go from B to D somehow, you need to go to E next. So B, E, D, right? A, B, E, D. You need to come up with that algorithm. Right? So let's go ahead and do that together. Right? Here's the path building. Path building. Right? So the input here will be Floyd's successor matrix. S, right? And 2 vertices, Vi and Vj in V. Right? And I want to output the path of least weight from V sub I to V sub j. And by the way, there are some caveats to a lot of this stuff. For example, does it work if you've got a cycle that's negatively weighted, right? So if I've got, say, for example, a cycle here with, say, 3, -4, and then this is a -8, right? And I want to know what's the shortest path to go from A to B. Well, what could you do? You could go around it as many times as you want, right? And get a smaller path, smaller path, smaller path. Now, does it, so it's ill-defined if you've got a negatively weighted cycle. But if you define it well and say that, well, I want only simple paths, right? Simple cycles, then it probably does work. Right? But in any case, I don't think any of the input does that to you. We choose all positive weights, right? All right, so we want to output this. Help me out. It's going to be almost exactly what we did with Dijkstra's, except that Dijkstra's was a predecessor matrix. We worked from the end point, Vj, and then we worked backwards. Here, we're going to start, this is a successor matrix, so we start at the beginning and work forwards. So my path initially, is going to be my starting point, V sub I, right? Starting vertex. Okay? And I need a current vertex here to be also V sub I. This is my current vertex. Starting at the beginning, I'm going to go to the next vertex, the next vertex, the next vertex, so that X here will end up being updated every single time. That means that I want a while loop, right? While I'm not at the end. In other words, while the current vertex is not equal to the ending vertex v sub j. Right? That means that you're not at your destination yet. Keep going. My next vertex will end up being whatever the successor matrix tells me it is. X and v sub j. Right? And again, annotate this. This is the next vertex in the path from X to Vj. Right? Yeah.
You can't get to it.
Then you would stop and immediately answer none. Right? What would the entry look like? Can you go from A to B? Yes, you can. Can you go from B to A is what I meant. Nope. So you'd immediately stop and output no path, right? None, right? In Python. We'll do the Python version here in a second, right? Otherwise, I'm going to update this to be my next vertex, and then I'm going to update the path to be whatever the path was before, appending X to the end of it. Again, it's a successor matrix. So I start at the beginning and work my way to the end. And that's why I'm always putting the next vertex at the end. That's in contrast to what we did with Dijkstra's, which was a predecessor matrix. We started at the beginning, and we always prepended. Right? And then I output. Sorry, go ahead.
Does it need to be like an if statement to check?
You could, or it's implicit in the, I guess, here, right? I guess you could if S sub vi vj is equal to none, right? Then output none, whatever your phi, right? Phi, whatever. Right. Okay. So what I've got over here, well, and now I'm gonna have to restart it, but while we're waiting for that to restart, let's go back to this right here, and let's clean it up a little bit. So, oops, there we go. So here is my successor matrix for a run of Floyd's algorithm on this, come on, and I've encoded that as a two-dimensional array in Python. My placeholders for no path are going to be none, right? Otherwise, I have used the single letters. Come on. There we go. So there it is. None BCD or BCBB, right? None BCBB, none, and then EE, et cetera, right? Now, remember that these are just associated with the columns, A, B, C, D, E, right? To actually use this in Python, I'm going to have to associate each of those columns with an actual number. So what I've done is I've set up a Floyd map here, right? Let's print that out. Print Floyd map. There we go. And run this. CSE 310, Python, Floyd, right? So again, what I'm doing is, if you want to know what the index of A is, it's 0. What's the index of B? 1, C, 2, etc. That's me setting up this map here. So that if you ask the question, you're not asking it with respect to A, B, C, D, E. You can ask it with respect to A, B, C, D, E, but ultimately it gets mapped to the first row, third column or something. Right?
You can get the IJ.
Right, exactly. Right, because like in the pseudocode, we were using v sub I, v sub j, k, et cetera, et cetera. Right? Now we're not going to actually program Floyd's algorithm. Instead, we're just going to do the backtracking here. This is the final matrix, the successor matrix for Floyd's algorithm on that one graph. Okay. So my start vertex, let's just go ahead and go with A, and my end vertex, let's go ahead and go with E, because that was the most complex path, right? Remember, going from A to B to E to D, right? And so it's going to look up each one of these entries in that matrix. Right? To translate that, or to translate the, can't believe I'm doing semicolons there. There we go. My path here will be, I start at the start vertex. Right? Okay. And then I need my current vertex here, and that'll be the start vertex as well. Again, what I'm doing is I'm translating this algorithm that we just made right here. Right? So there are the first two lines. The start vertex and the start vertex, the current vertex will end up being at the start vertex as well. While the current vertex is not at the end vertex, right, I will update the current vertex to be whatever the successor matrix tells me. Right? And then I will make sure that I append p.append x to the end of it, printing out the path at the end. Okay. Now, the question is, how do I translate this all to the successor matrix up here? Right? Could I do something like this? Floyd, so say x and end. Right? Remember, that's what I did over here. Right? X, and there's the ending vertex v sub j. Right? The problem is, what are those? They're strings. Right? Strings are not indices. That's why I set up this map here, right? This Floyd map. Okay? So, index of x. Let's go ahead and call Floyd map of x. Right? Index of end is equal to Floyd map of end. Now what I can do is use those indices. Index of end. Yeah, go ahead. Yeah, it never changes. So if you want to, you can do it up here. I wasn't even going to do that. I was just going to not even store them in variables. I was just going to put them right in here directly. Fewer lines of code, but you're right. The end index never changes, so I'll go ahead and just do it once instead of every loop. Right? Now, if this was correct, remember, what should it be? We go from A, B, E, D. I don't know. Darn it. What's wrong? Path. Oh. It's just a spelling. There you go. A, B. Oops. What did we do? A, B, E, D. Yeah. Why didn't we get the last one?
Well, it's not n, so it doesn't. Say it doesn't give another.
That's not what. Okay. We could just do one more p dot append end. Right. Is that going to be enough? Oh, no. What am I doing?
Oh,
I asked the question about E. Of course, the ending index is going to, ending one is going to be E. I meant to ask it about D. So it should be A, B, E, D. Right? There we go. A, B, D, E, D, excuse me. What about, what else could we do? What about A to E? No, I guess we that's not that interesting. A to D? That's what we just did. D to A? That's a good question. Can you do it? D to A? Here's the graph. Can you go E to E to... Nope. So what should we expect here? None, but what are we going to get? That's a good question. This is where that first line that you wanted to write comes in, right? Okay, so none. So what should we do? Probably put this into a function, generate path, right? And we'll have the start, end, right? Put all of this over and return P, right? Sorry, what? Thank you. And then P is equal to generate path of start end. And we can still print it out here. And then we add in one line of code here, right? Index of end. If No, I want the indices. And if Floyd of index of x, so I'll just go ahead and cut and paste this to the index of end. So I'll go ahead and cut and paste this. If that's none, then return none. There we go. And now the answer should be none, except that if you print none, is it going to work? Okay, yeah, well, yeah, none. Let's make sure that it still works by going from, what, A to D? Did I break anything? Nope, it's still good. You can do a whole bunch of other error checking here. For example, what if it's an invalid value? For example, what if I want to go from A to X? I wonder what happens. You're gonna, in your map, you're gonna get none, and when you use none as an index, that's going to be a runtime error. Yeah. So, to do more error checking. To do more error checking. Dot, dot, dot. But that's just boring boilerplate stuff. All right. Any questions? We could do something like this, right? For start in a, actually no, I've already got it right, in vertex names. There we go. For start in vertex names, for end in vertex names, generate all of the paths. All right, this is what you're going to do in your assignment, right? And print in a nicely formatted manner, going from start to end. That path should be P. Can I do that with a whole list? Let's find out. Yep, there we go. So go from A to A, none, because of course you just stay there. Going from A to B, you just go A to B. A to C, A to C. A to D, you go A, B, E, D. That's the one that we were playing around with. What's something a bit more interesting? There's something interesting. C to E says C, D, B, E. Right, let's go ahead and take a look at what that looks like. E to, what did we say? E, C to E. Right, so
That's only
C to E. Right. Initially, it looks like, well, you go to D, all right, and then you're stuck. You'd have to go over here to B and then over to E, right? Is that right? 5, 9, 11. Right. So C, D, B, E. C, D, B, E. Yep, looks like it. So generating paths. By the way, I don't have the data here, but how would I determine what the weight of that path is without having to go over the path and sum everything up? That's the purpose of this distance matrix. Right? There it is. There's that 11 that we were talking about. Right? Going from C to E, 11. Right? What would you do in Python for infinity? Oh, math.inf, right? Exactly. Right. All right, so 10 minutes left. Anything? Any questions?
There's any way to, if you made like the successful matrix using maps, and if you could just like get A instead of having a second
Yeah.
mapping.
Yeah, you could do that. The map, however, would be combinations. So Floyd successor map would look something like a combination of going from X to Y. Where do you go to next? Whatever the successor is. So you would need to have two tuples going. That's how I would do it, at least, right? We could do this really quickly, right? Here, there's the key value pair for. How do you do a list comprehension for a two-dimensional list? for row in Floyd, for column in Floyd. Now I need to rename the row X and Y. And then instead of the successor, it would be Floyd sub X, Y. There we go. Print Floyd successor map. Let's find out. I'm excited to see if that worked. Nope. List indices must be integers or slices. For
X, Y in Floyd?
X and Y are the
yeah,
you can't do
how do you do two-dimensional? I know that you can do it.
X and Y for one Floyd?
Well, I want to use a list comprehension to do like for each combination for each X comma Y. Oh, you know what? This is just a regular matrix, so we could just go what for I in range of length of Floyd. Right.
How's it square root?
Yeah, it's a square matrix, so we could go. How do I do two combination though? We've got 9 minutes if we really wanted to think about this. Python list comprehension. Fix my spelling 2D matrix 2D array or 2D list over a 2D array. For a list of lists, there we go. Something like that. Let's use that as an example. All right. So you create another list here for sub in list. That's still I don't like that indexing without a loop. Flat list. Iteration tools. You could bring in a library to do it. Any suggestions? For X, sub X for X in 0 through 7. So for X, no, let's go with Floyd of X for X in range of, let's just go 5 for now. There. I'm not comprehending it. Darn it. I'd have to think about this. I don't want to waste everybody's time. Unless you've got a solution really quick. No.
Because what I was thinking originally was like, you know, now, where values like A, B, C, D, and E, and then each of those map to another map. But I think it would be a weird way to do it because I think like the inner maps would just be like B to B, so that you
Yeah.
B to different value B.
I wouldn't do that. Yeah.
It'd be a weird way to do it.
I would I was thinking something like this where it goes to the successor, right? You give me the combination A, B, and I'll give you the successor for that. So that then you can go successor to B, and then that maps to the next successor, right? All right, so to do over the weekend, come up with a map comprehension for 2D or 2D lists. Right? I'm gonna do it. Say what?
This is where Python comes into column.
Exactly, like I said the other day, right? When you're doing something simple and straightforward, it's excellent, right? But I mean, look at this one guy's solution. Like, The whole point of having a list comprehension is that you can read it out in plain English, or you can, grok it right away. And if you are having to bend over backwards to do something like this, then it loses its value, right? So the second you're trying to do something complex like this, then it's going to be terse, right? It's going to be small, but to understand it, to read it, to even write it that first time, you might be able to write it the first time, but then you come back and that's not readable at all, right? It's just a 5x5, so Floyd sub xi.
I'd have to copy the whole thing now.
Okay. Here, let's go ahead and sign off here for a second. But otherwise, have a good weekend. We're done with graphs.